All right, so here's another problem where we will, try to use torques and stuff to determine some equilibrium conditions. Okay, so this is a ladder that is at some angle, and what you're told is that the only place the ladder experiences any friction is on the floor. We'll assume that the wall is frictionless. Okay. And the question is, what is the largest angle, or rather the smallest angle theta this ladder can make before it starts to slip on the floor? Okay, and the coefficient of static friction is given as mu. Okay, so let's address this problem. As usual, the first thing we'll do is draw a free body diagram. Okay, at this point, what I'd like you to do is pause the video, draw your forces, okay, and then come back and verify that your forces match mine. Okay, so take your time and do this. All right, now I'm assuming that you did this. You took your time, you drew everything out. I'm going to do the same. So the first force I'm going to draw is the weight of the object. Okay, the weight points down. I'm going to call it mg. It's at the center of gravity, center of mass of the thing, and it is at a distance of L/2 from either end of the rod. Okay, so that's one force. The other force we have is the force of contact at the bottom. So I'm going to call this Fn1. We know that the force of contact is always perpendicular to the surface, and that's where it's pointing. Now at the bottom, we also have the force of friction. Now since the rod is trying to slip to the right, the force of friction will try to stop it, and it'll be to the left. So it'll be simply mu times Fn1. Now, we also have contact at the other end, and this force is going to be equal to Fn2. Now, because the second contact is frictionless, we do not have any other forces acting on that end. Okay, so we're going to use these forces along with our conditions for equilibrium, static equilibrium, to calculate this angle theta. Okay, so let's do that. Let us equate all our forces along the x-axis. Let's set up the forces along the x-axis to be equal to 0. Okay, so this condition tells us that Fn2 is equal to mu times Fn1. Right, so it makes life easier. We have one equation. We play the same game along the y direction. We say that all the forces along the y direction are also 0. Now, in this case, there are only two forces along the y direction, and those are simply Fn1 pointing up and mg pointing down, and we see that these two are equal to each other. Now, because these two are equal to each other, we can also now just simply write Fn2 as mu times mg. So it simplifies a lot of things for us. Okay, so our next thing is now to calculate the angle theta. So in order to do that, what we will do is take torques about points. Okay, now we can choose any point that we want, but in order to do the calculation well, we will choose, say, point A, which is one end of the rod. Okay, I will take torques about that point A. Actually, I think it would be easier to take this as the point. Let's take the bottom B, because you see about A, we have three forces giving us a torque, mg, mu Fn1 and mu Fn1. So why make life difficult for us? Let's make it simple. Alright, so let's take torques about B. Okay, so what we'll do is we'll take net torque is equal to 0, but we'll do this about B because I think it'll be easier to do it about B. Now about B, clearly Fn1 and mu Fn1 do not exert any torques, so that makes life easy. So the only forces that are exerting a torque are Fn2 and mg. Now we will use the definition of torque. We'll use the R perpendicular times F definition, and you'll see that it actually simplifies life a little bit. Okay, if I were to extend Fn2, okay, then its distance, its perpendicular distance from the point B is simply one of the sides of this right angle triangle, and the way theta is labeled, okay, we realize that this distance is simply going to be equal to L times sine of theta. Okay, so that makes life easy. On the other hand, mg, okay, the perpendicular distance of mg from B is equal to L over 2 times cosine of theta. Okay, so you can work this out and obtain these two results. Now that we have our distances and have our forces, we also notice that Fn2 will produce a clockwise rotation about B, whereas mg will produce a counterclockwise rotation. So we can use all these things and write now our net torque about B as mg times L over 2 times cosine of theta is equal to Fn2 times L times sine of theta. But we know that Fn2 is simply mu mg, so this tells us that mg L cosine theta over 2 is equal to mu times mg times L sine of theta. A lot of things cancel out. You'll see that m and m can be factored out, g and g goes away, L also goes away. So we are essentially left with cosine theta, half cosine theta is equal to mu sine theta. Let's move all the thetas on one side and everything else on the other side, and I end up getting 1 over 2 mu is equal to sine theta divided by cosine theta. Okay, and we can write this instead as 2 mu is equal to cosine theta over sine theta, which is equal to cotangent of theta, and therefore we end up getting theta is equal to cotangent inverse of 2 mu. So this is the condition. This is the smallest angle, okay, at which this ladder will continue to remain at rest. Any angle lower than this and the ladder will start to slide. Okay, so hopefully you understand this problem, and try doing the whole thing and make sure you get the calculation. Now if you are able to get this all by yourself, okay, try out these two challenge problems. Okay, and in one of the future videos I will leave out the answer for these cases. Okay, so let's say now that we have the same rod of mass m and length L, and let's say we have coefficient of friction mu at the bottom, and we also have mu here. Okay, so in this case, what do you expect this minimum angle to be? Okay, work it out and compare it with the theta that you found, okay, out here, and see whether it makes sense or not. Obviously you expect it to be smaller than this theta, okay, because there is additional friction now. So that would be one problem. And then the second problem to solve would be, if I have once again a ladder, okay, resting out here. Let's say I give you the friction here and here, they're both the same. And now I also give you the theta, and let us say that the mass is m here, okay, of this rod, and this length is L, and we ask how far up the ladder can a person of mass 10 times m travel. So how far can they travel up this rod such that it will continue to remain in equilibrium? Okay, so think about this, and let's see what we can do. Okay, all right, good luck.